So if there are no questions, then let me start by presenting. Oops, just hold on. Okay, I'm back. So let's start with expanding this out. So where were we last time? Just remind me of that. How much have we done so far? Yes, any
modes in vibrational modes in a molecule. We start with squaring.
Oh, we were okay. We have just given that as an example of how to figure out representations and so on. We're going to take a look at that in detail later, of course. But first, what we need to do is take a look at how much of the theory have we covered. What have we covered so far? Have we done direct direct product representations yet? Or things like class matrices and how to use class matrices to find out, I can say, find out the characters. Yes. Projection operators, have we done any of those things? I don't exactly remember, but I think what I did was I just gave you the squaring as an example of how you could use these results that we have derived so far. But right now what we want to do is we need to stop looking at the specific example of a particular application, go back to the full theory, and once we have the full theory in hand, then come back to that application again and see exactly what we can use it for. We have already seen that we at least can do quite a lot. For example, we found that we could at least find out that the representation was reducible. We could find out how to reduce it, and we indicated how you could interpret at least some of these irreducible representations. In particular, one two-dimensional one as the two translations, another one-dimensional one as a rotation, and the rest had to be vibrational modes. So we also talked about what kind of degeneracy you would expect among the eigenfrequencies from here. But frankly, we have not justified any of that. We need to go through a full theory of molecular vibrations to justify that. But let me just go back to the full theory first. Let's get all the background in hand first, and then we will come back to this and look at this in some detail. So first, what we need to do is take a look at some more results from representation theory. And one very important kind of representation which is going to come up over and over again is, oops, what is this? This is the highlighter. Okay, is something called the direct product of representations. And you have actually seen direct product of representations several times in quantum mechanics, at least. In fact, the whole issue of addition of angular momenta that you did was really and this whole bunch of Clebsch-Gordon coefficient calculations that you did were really a special case of the general theory of Clebsch-Gordon coefficients, which is for the direct product of representations. let me just remind you of what you had there. So this is just a reminder of QM. So what you had essentially was your states like these, which when they underwent the rotation, they translated, this changed because of the fact that for each single value of J1 you end up with an invariant subspace. Now I'm just quoting results which you must know in some language or the other, maybe not precisely in this language. I don't remember whether somebody taught you this, but this is what you are going to get. So you're going to get M1 prime, some matrix which depends on J1, depends of course on the rotation, M1 prime M1, J1 stays the same, M1 prime. So this of course is just saying that these angular momentum eigenstates, they form a basis of a space. If you rotate your coordinate system, what happens is U of R, a unitary operator, gets to act on J1 M1, and that produces a new element in that space. So that element can of course be decomposed in terms of the other basis vectors on that state. That is in terms of J1 M1 prime, where M1 prime of course goes all the way from minus J1 to plus J1. And of course, if we did the same thing to another state, J2 M2, you will get M2 prime equals minus J2 to plus J2. Some matrix, which we call the rotation matrix, dJ2 R M2 prime M2 J2 M2 prime. So this is fine. This is just saying that if you rotate your coordinate system, your basis vectors are kth vectors are going to change because of that. Now, if you look at this state, which of course is really nothing but a tensor product of these two states, now you end up with a total of 2J1 plus 1 into 2J2 plus 1 states, right? And these form the basis of this direct product space. Tensor product of these two spaces. You have two spaces here, V1 which was spanned by J1 M1, V2 spanned by J2 M2. This is really the basis of V1 cross V2. I hope all of this is familiar to you. Is it?
Yes, sir.
No? Okay, great. So when you rotate your coordinate system and ask the question, what happens to the tensor product space? Of course, you answer this by looking at what happens at the basis vectors of the tensor product space. If you know what happens to the basis vectors, you know what happens to every vector. And what will happen here? What will happen here will simply be J1 M1 will rotate on its own, J2 M2 will rotate on its own. So this one will pick up a factor of DJ M1 prime M1, this one will pick up a factor of DJ2 M2 prime M2. So the overall thing will pick up and this is what you're going to get. Right? Now, what this really says is that these are the basis vectors of your new space. Okay, I should really not have done that. Anyway. So these vectors here are the basis vectors of the direct product space, and you have just found what U of R do to the basis vectors, and you get these as the matrix elements in that basis vector space. So what you see is that if you want to talk about the new matrix in the direct product space corresponding to U of R, corresponding to the rotation R, well, it sort of gets a bit more complicated simply because it seems to have 4 indices. After matrices should have only 2. But notice what you really have is M1, M2 here is really a single index. Not the, of course, this doesn't mean the product M1, M2. It just means M1 and M2 together. They form an index which qualifies a basis vector of this space. Just to point out how many M1, M2 pairs are there. M1 takes 2J1 plus 1 values, M2 takes 2J2 plus 1 values. So M1, M2, the number of pairs of M1, M2 is 2J1 plus 1 into 2J2 plus 1, which exactly spans the entire space. That's how big the basis should be. So M1, M2 is a single index. On this side you have M1 prime, M2 prime. That's also a single index. So basically you are talking about 2J1 plus 1 by 2J2 plus 1 dimensional matrix. Not by, into 2J2 plus 1, that's the size of the number of rows and the number of columns of your matrix that you're talking about. And this has to be, of course, dJ1 R M1 prime M1. These are, of course, genuine ordinary single index matrices, the way we usually talk of them. R M2 prime M2. So this is basically how you form direct product of representation matrices, or in general how you form direct product of matrices. If you take two matrices A and B, say both of them are say M by M for the timing, let's keep things simple for ourselves. So the direct product A cross B will actually be an M square by M square matrix. And how do you define that? You define this by saying A cross B has elements I prime j which are indexed. The rows are indexed by pair of numbers. So are the columns, and this is given by A cross B I prime I J prime J. Okay. So everybody is familiar with this, right? Direct product of matrices, how to actually form them and what they look like in calculations. Right?
Sir, did you mean A, I prime I, B, J prime J?
Oh yeah, of course I meant that. Sorry. That was a stupid thing to write, of course. This slide makes no sense. I wrote the same thing again. It is, or rather I did something very different and it should really make no sense. You're right. This is what I meant. A I prime I, B J prime J. So once you get used to the fact that you're using two indices to indicate a single row and two indices to indicate a single column, it's really pretty straightforward. Okay? But the important thing in context of group theory is this. Just like we talked about rotation group representations, for an arbitrary group, say what you have is if D1 and D2 be two representations, and although rotation is not a finite group, I'm going to talk about finite groups only for the time being as we want before. The reason why rotation can actually sort of give you very similar results is because rotation is what is called a compact group. We are going to talk about that later. Okay. Group G of dimensions, let's say small d1 and small d2. Then consider this matrix DG, which is of dimension D1, D2, and which is defined to be this. You just take the matrix corresponding to G in the representation D1. You take the matrix corresponding to G in the representation D2, find the direct product, and then you get a new matrix. And it's trivial to show that DG1, G2 will be DG1, DG2. Okay, so let's give this as a homework. Use the definition of the, basically this follows from a simple part of the definition of the direct product matrix. That is, if you take the matrix A cross B and take the matrix C cross D, where A cross B and C cross D are of the same size, A and B, C are the same size, B and D are the same size, then you can easily show from the definition itself that the matrix product is given by this. And using this result, this is a general result from linear algebra, this is a result for matrices. But using this, you can easily show that the D which I form by forming the direct product of D1 and D2, we call it the direct product of the representations D1 and D2. But by that, what I mean is for every group element small g of capital G, I take D1G and D2G and form their direct product matrices to get a new matrix, which is D of G. So once we do that, it's rather straightforward to see that this is what is going to come out. Now, let me just point out one more thing. It is a trace of A cross B. What do you get? Of course, A cross B, you need to take A cross B's II, JJ element and sum over I and J, right? But that's A's ijth element sorry, did I mess up? I did mess up. Sorry, I completely messed this up. What you need to take is a diagonal element of A cross B, which is actually ij is a single row, remember? And you have to take it from the same column. So ij is one row, ij is the corresponding column. So this is what you need to do. And so this works out to be, of course, and sum up over both I and J, of course. So this works out to be AII BJJ, right? This is what A cross B, remember, that's how the direct product matrix is calculated, sum over both I and J. So this really is trace of A into trace of B. Once again, nothing to do with representations or group theory. This is a standard result in matrices. The trace of the direct product matrix is the product of the trace of the individual matrices. And that immediately tells me that we have a very simple result for the direct product representation, which is chi g, the trace of dg, must be so if you have any two representations and you want to form the direct product representation, you just find direct product matrices. Characters are even simpler. You just take the characters and multiply them. That's it. Okay. Now, why is this so important? It's simply important for the same reason why direct product of rotation operators is important in the rotation case. Basically, if you have a system composed of two pieces, each of which are invariant under the action of a group operation individually, that is, say piece A changes into some form of itself under a group action, piece B also changes into some other form of itself. Okay, but when you take A and B together, basically the description has to be the direct product space, and now this gives us a new bigger representation of the full of the group, which is simply by taking the direct product of individual representations. What's useful about this? Because, well, in physics, many situations can be described where individual pieces transform simply under groups. The overall whole system essentially transforms under the direct product of those representations. So Physically, this is very important simply because in physics there are many situations where you can think of an overall system as being made out of individual pieces. And typically smaller pieces are easier to handle. But now, this tells me how to find the characters. This also tells me you can easily find out whether things are reducible or not. Okay, and then find out reductions, right? So let's say we had this symmetry group of the square that we worked out the other day, right? We had did we do that? The characters for that? We did that, right? We found out the character table for that, didn't we?
Yes, sir.
Okay, let me see whether I can find the table. Did I save that file? I don't remember. Might be this one. Oh, I have to save this one. So let's save this first. Does it open two things together? Okay, so now this one is open. That was a last week's class. The character table should be written somewhere here, somewhere in the middle, somewhere. Hopefully, yeah. This looks like the character table. Let's see. Yeah, this was the character table, right? This was the messy thing that we have here. 5 rows indicating the fact that there are 5 classes and hence 5 characters. 5 classes for the column headings, 5 characters here. Good. So this is a table that we do have. Let me try one thing. I hope I can copy this. Yeah, I think I should be able to paste it here. I'm still new to this app, so I'm not very sure whether I can do it. Let's hope I can. Yeah, great. So I have the character table for the symmetry group of the square right here. Okay. So suppose I have something which transforms like, I don't know, which one would you want? Let's say some okay, let me just add one page. So this is the character table, 5 irreps, and let's say we form, we have a 3-dimensional representation which I forgot to write down, right? From the x square xy, so that was also in the last one. Anybody remember what that was? That was, I guess, 3. Of course, this has to be 3. I hope this is making sense to people, what I'm saying.
Three, 3, and there were last 2 pages for 1, I think.
Okay, was it even right? Okay, this was a one with which we did some manipulation. So we were 3, 3, 1. It was 1, 1, minus 1, right? This is the correct one. Of course, we could again play the same game as trying to guess at it and then figure out that we are messing it up. But this, I think, was the representation D. Okay, so this is one representation, and let's take as another representation. Let's take D cross D. That will be a bigger representation, of course. What will the dimension of the representation be? 9. Of course. And we'll have characters 9, 9, 1, 1, 1. Right? Is that okay? Because you just multiply characters. So 3 times 3, 3 times 3, 1 times 1, 1 times 1, 1 times minus 1. So 9, 9, 1, 1, 1 for D cross D. That's all. That's it. Right? So let's take a look. How would this reduce? So quickly, can you tell me what will I get here? M1. You just form this group sum 9 times 1, 9 times 1. Just remember there are twos, the weights of twos for all the others. So 2, 2, 2, 9, 9, 18 and 2, 2, 2, 6, 24. Right? So what is M1?
3.
M2? Quickly, what is M2?
2.
I hope everybody else is following. M3, well, M3 should be exactly the same calculation. In fact, M4 should also be the same calculation. And what is M5? By this time, I should know that M5 has to be 0, right? Because I've already exhausted 9 dimensions. M1 is occurring 3 times, M2, M3, M4 2 times each. Each of them are 1 dimensional. So 9 rows and 9 columns of the matrices for D cross D is gone. Of course, M5 works out to be 0 simply because 9 times 2 plus 9 times minus 2 is 0. So this is a pretty straightforward calculation, right? This is something which is going to turn out to be very important in the long run for applications, because there are many situations where direct products will come in, where you have products of two different things, one of which transform like one representation, another which transforms like another representation. So the overall thing, the product will transform like the direct product representation. And once you have that, you have to actually try to get the calculation done from there. That is, you try to reduce the representation first, and then then try to draw physical conclusions from that. We have not reached that part yet, how to get to the physics from it, but at least we know how to handle this calculation. Just to check whether everybody is with me, let me just do one thing. Instead of this one, let's just do. So once again, 2 systems, one of which transforms like D, the other transforms like the irrep D5, the last row of that column. So quickly, tell me the characters here.
Uh, 6 minus 6 0
0 0 0. Good. Now tell me what M1, M2, M3, M4, M5 will be. M1 will be? That's the easiest. Even M1, M2, M3, M4 should be pretty easy. Right? What should it be? M1, M2, M3, M4, all of them should be 0. Does that mean this is irrep? After all, there's only one irrep left, D5. So does this mean that this D cross D5 is an irreducible representation? Of course, it can't be, right? We already know that the largest irrep which this system has is of size 2. This is size 6. But it's rather easy to see that all this means is that M5 must be 3. So D cross D5 is actually this, the direct sum of the 5th irrep taken 3 times, right? So there are 3 copies of D5 hidden in D cross D5. Okay. So this is one important issue gone. This is a pretty easy calculation, but which will have far-reaching consequences in the long run. because this is a huge amount of application behind, and which this will pertain to. Okay, another very important issue, once again, not very important for the mathematical point of view of group theory, but very important for physics, is the issue of reduction of symmetry. And let me try to explain what that is sort of is by starting from our square again. This of course looks pretty bad as a square, so you have to pretend that this is okay. Let me just try drawing it a bit better. Although I'm not very comfortable with this, so oops. Okay, let me just take the help of this. So let's pretend that this is a square, and let's say something has happened to the square and has got distorted. It got distorted into a rectangle. Say maybe somebody squeezed it or something. Because the first thing that happens as a result is the symmetry gets reduced, right? So this had 8 symmetry operations. Oops. The identity, then you had 2 reflections like this. 2 reflections down the diagonal. You have to pretend that all my lines are going through the center of the square, and they are really straight lines, CD, and we have this 3 rotations FGH, a 180 degree, 90 to 70. Now all these, some of the symmetries survive, some don't, right? So which one survive for the rectangle?
E, A, B, G.
E survives, of course. E survives anyway. A, B, and G. Right? So now, now it's very easy to check that this. Okay, if you were to multiply 2 elements of the surviving group, if you multiply E with anything, it doesn't matter which order you do it in, right? Whether you put it on the left or right, you get the same result. G with okay, A with B and B with A, both are what? What do they have to be? G, right? Because have to be rotation, and rotation through 180 degrees, because the lines A and B are separated by 190 degrees. It's very easy to check that this is an abelian group. Okay, no matter which way you put the multiplication in, you all says A times G has to be another reflection turned through by 90 through what? What is A times G, by the way?
B.
Good. What is B times G? What is G times A?
B again.
B again. Good. Now, the point is this original square had 5 errors. Okay? How many errors does this one have? Quickly, this is something which you should be able to say off the top of your head. How?
Sir, can you
The original square had 5 irreducible representations, right? How many does this one have?
3.
3. Why did you say 3? Which ones are the classes?
The E will be 1.
Okay.
G will be 1. D will be 1.
G will be 1 and
AB will be 2.
are you sure? Why do you say AB should be 1? Why are you saying that? Just explain your reasoning to me.
You can write B is equal to A inverse BA. So A and B are conjugate to each other.
You can write B equals A inverse BA.
Yeah, because AB equal to BA.
You are saying that you can write B equals A inverse BA. And you are saying that's because AB equals BA. Are you sure? What is A inverse BA? By your logic, it's A inverse AB, right? Okay, that's fine. So you get B equals B. So what does that show you? Does it show you that A and B are conjugate, or does it show you that B is conjugate to B? Remember, the conjugation relation is G1 is conjugate to G2 if there exists a G such that this occurs. These two elements are conjugate, not G and G1, right? All we have managed to show here is a trivial result that B is conjugate to itself, which we already knew, right? You didn't have to look for A for that. You could have done that using E. And it wouldn't have mattered whether the elements commute or not. Here what I have told you is that this group is abelian. So can you now let me just point out one thing. We did say that reflections can be in a class of their own, rotations can be in a class of their own, but there were restrictions, right? Any two rotations could not be in a class of their own. Similarly, any two reflections could not be in a class of their own. In this example for example, A and B were in a class, C and D were in a class, but the two were not in the same class. Why was the case? Why was that the case? Geometrically? Could of course say mathematically, because I couldn't find a G such that A is G inverse CG. That's correct. But what is the mathematical reasoning that would, what is the geometrical reasoning would tell you that AB and CD have to be different? Yes? That was one thing we discussed quite a lot in the last class, right? What tells you that these two are in the same class and these two aren't? I hope I'm still connected. So it seems like what I should say now is what A.K. Hangal said in Sholay. I hope you understand what I mean, or are you too young for Sholay? What's the quote I'm going for?
I haven't watched Sholay, sir.
You haven't watched Sholay, so it's wasted on you. Anybody here who has watched Sholay, or am I really a dinosaur?
I mean, no, sir. People do. It's common even in our generation.
Okay, so anybody else who can say what I was aiming for, which particular quote? No, that was not. Okay, so you know that quote. That was not A.K. Hangal, by the way. That was Abjad Khan. That's Gabbar Singh. This was Itna Sannada Kyun Hai Bhai? Of course, not delivered like this, delivered the way A.K. Hangal, being the old man that he was, did it. But anyway, so Sannada Kyun Hai? Don't you remember anything of this? why AB are in the same class, why CD are in the same class, and so on?
AB are reflection,
AB,
parallel.
true, AB are reflections, so are CD.
CD goes through.
Yeah, sorry, yeah, but they're also reflections.
CD keeps the vertices invariant. It just changes the opposite vertices. AB change all.
No, fine, but why are you still saying that they can't be in the same class? Being in the class doesn't mean that they do the same thing, right? They don't. A and B don't do the same thing.
There is no element to convert A to B because they are different.
You are right, but A to C. There is no symmetry element here which will convert the line of reflection A into the line of reflection C. That would require a 45-degree rotation, which is not a symmetry element of this particular group. Whereas there is a symmetry element which converts A to B, a 90-degree rotation, right? That is why they are in the same class. Similarly, F and H are in the same class because they are actually rotation through the same angle, 90 and minus 90. And there is an element in the class G which actually changes the axis for F into the axis for H. Having said that, can you see now why A and B cannot be in the same class for the rectangle? The 90-degree rotation, which converted the line for A into the line for B in the case of the square, is no longer a symmetry element of the rectangle, right? For the rectangle, there is only A reflection in this line, there's B, this reflection, and a 180-degree rotation. Yeah? Okay. So there's no way in which A and B can be in the same class. And there is another easier way of saying that, or non-geometrical, more faster way of saying that, which is, as I claimed, this is an abelian group. Now, what do you know about abelian group classes? If a group is abelian, then take any element from the group, take any other element, let's say G prime, and form this. What are you going to get? If the group is abelian, what will come out? What is this going to be?
G.
Always, right? Because G can always jump across G prime, and then G prime and G prime inverse cancel each other. So because it's abelian, this group, all the classes have to be singleton elements, only one element sitting by its own, because any conjugacy operation you do has to give you just that element. That's true for all abelian groups. Forget about rotations, reflections, or everything. For any abelian group, each class is a singleton element. For the same reason why the identity is a identity class is a singleton element for every group. The identity commutes with everything. In the abelian group, everything commutes with everything. So there's no way you can change an element by conjugation. So you get singleton elements only, which means the number of classes is exactly equal to the number of elements. So that means here you had 5 classes. So 5 irreps. Here you have 4 classes. And how many dimensions? How many irreps? Of course, 4 irreps. And there we are seeing the 5 irreps where 1, 1, 1, 1 for one-dimensional and 2-dimensional representations. These are the dims of the irreps. What would be the dimensions of the irreps here?
1, 1, 1, 1.
1, 1.
Has to be 1, 1, 1, 1. Right? Okay.
So in one application of the orthogonality theorem, you
for an all abelian groups have one-dimensional irreps. Right? So that was a general result. And here, of course, if you don't want to use the general result, use our latest result that you need 4 squares which have to add up to 4. The only way you can do that is, of course, 4 ones. Well, that's really not true, right? Is it true? Is that the only way you can add 4 squares to get a 4 is 4 ones? Is that correct?
2200.
2200 is not 4. 2200 is 8. You mean 2 square, 2 square.
Right.
But you are close. You could have 2000.
Yeah.
But 0 is not allowed, remember? These are dimensions. The squares you are adding are squares of dimensions, and dimensions cannot be 0. You need positive integers whose squares are being added. So that's why 2000 is not even a possibility. 1111 is the only possibility. So even if you did not know that application of the GOT, it can still be derived from, which ultimately from GOT anyway, because all these results we have actually all of them come from GOT. But that was a direct application. Here we have this result which says that sigma di squares have to be equal to order of the group. Anyway, so now tell me one thing. Now this representation that we have for the square, okay? What is that? Take any representation for the square, which is you do some operation on the square stays the same. Okay? Now that of course will give you 8 matrices, one for every group element. Now if you pick out from that just the group elements for E, A, B and G, pick out the 4 squares which represent the symmetries which still survive for the rectangle. Will that give me a representation for the rectangle? That is representation for the rectangle symmetry group. That's a more precise thing to say. So this is a big group with 8 elements. Any representation, of course, depending on what you are talking about. If it's a linear representation, it's a linear operator, one for each element of the group. If it's a matrix representation, one matrix for each element of the group, and so on. You just picked out from that the 4 objects which represented E, A, B and G. Will that also give you a representation for this one? Will that happen? Yes or no?
So the square has a 2-dimensional representation. So if you don't consider that, then
wait a minute. Are you saying the 2-dimensional representation will not work for the 2-dimensional representation? That's what you're saying.
all the representations of the rectangle are 1. So like they are 1-dimensional representations. But in case of a square,
okay.
there's a
let me correct you there. Are you saying all the representations of the rectangle are 1-dimensional? Are you saying that?
Oh no, there can be two representations.
Yeah. So to be very careful. What you are saying is all the irreducible representations of the rectangle are 1-dimensional. You can have 75-dimensional representation on a rectangle, for the rectangle symmetry group. They will be reducible, of course. But now I am asking, forget reducibility, or forget this issue whether it's reducible or irreducible. Take any representation for the symmetry group of the square. Pick out from that representation just the 4 elements which still correspond to the surviving symmetries. Will they give you a representation on the rectangle? Yes or no? Further, you have to realize one thing: the symmetry group of this rectangle, is this a subgroup of this bigger symmetry group? Yes or no?
Yes.
Is this a this is a subset? That's obvious. Is it a subgroup?
It is a subgroup because the EABG themselves form a group in the first place.
Okay, it was originally a subgroup in the context of a bigger group, but you can also think of it this way that after all, what you need to check whether it's a subgroup. You have to check whether it's a group under the same set of operations. Okay, right? That's important. So this new group may be abelian, fine, but if you multiply A with B in this group, do you get a different result from what you got in the other group? So if you multiply AB here and AB here, do you get two different results?
Same
You of
result.
course have to get the same result, right? You're doing the same operations, one after the other. So this is a subgroup, right? But if it is a subgroup, then same multiplication law holds within this subset as it held for the bigger group, right? Of course, all you are saying is if you multiply elements of EABG, it will not go out of EABG. You will not get C, D, F, or H. Fine, but at least within that subset, the same multiplication rule holds, right? So if you took the representation matrices DE, DB, DA, you forget the rather stupid order I wrote this in. You took these four matrices and multiplied, say, DA, DB, DA. What would you get? You will get DBA. I'm talking about the representation matrices for a square, right? You will get DBA, right? Because it's a representation matrix, and because BA is G, you will get DG. But BA is G also for the rectangle, or also for the rectangle symmetry group. So it's sort of obvious, if you think about it, that any representation of the square will also give you a representation on the rectangle. By taking a subset of the representation matrix elements. Is this issue clear, or do I need to clarify this further? I want a yes or a no.
Yes, sir, it's clear.
Okay. Now, let me also tell you why this is so important in physics. In physics, very often it happens that you had a big symmetry group, and somehow because of some reason, it gets broken down. When it gets broken, does it mean that there is no symmetry left? Of course, usually it doesn't mean that, right? Usually when you have a broken symmetry, some symmetry is also left. That symmetry is a subgroup of the original symmetry group. In fact, many of you may have worked in broken symmetry in particle physics. Essentially, that's what this is. A big group gets reduced to a smaller subgroup. So the original symmetry gets reduced. The important question is, you had irreps for the original group. What happens to those? Or you had representations for the original group. What happens now? They're still representations. Okay. But, and this is critical, this is what, of course, you were alluding to before. You had 5 irreps in this bigger group. You have 4 here. And that obviously means that, and each of them one-dimensional, that of course means that at least the 2-dimensional irrep has to be reducible. Okay? And this actually has huge physics consequences. Irreps for a bigger symmetry group can become a reducible representation for a smaller group. If you think in terms of particle physics, that might, well, that is basically why the photon and the W bosons, for example, split. Okay. But this is, the context really is what was essentially the same particle before, because it was sitting in a single irreducible representation. Now, after the symmetry breaking, is no longer the same particle because you don't have any symmetry operation which takes you from one state to another state in between. Do you get what I'm saying? Of course, when we apply this directly to particle physics, this will be more clear. But what I'm really trying to say is something like this. If you have symmetry operations which changes one state to another, you will not really call it states of 2 different particles, right? Say if you went from, let's just say, you went from one Lorentz observer to another Lorentz observer. The states change, right? But are you going to say that there are states for 2 different particles? Of course you won't. You will say that there are states for the same particle looked at from different observers, right? Similarly, any symmetry operation that you can do, if it's the symmetry of your theory, you're doing a symmetry operation, one state changes into another. you will just say there are different states pertaining to the same particle, which may have multiple states describing it. And that's not a surprise, of course, because see, the electron has to spin up and spin down and so on. But the point is, bigger reducible representations, bigger irreps for the original group may very well break down to smaller irreps once symmetry is broken. And that is the reason why a particle which has really different states of the same particle in the original fully symmetric theory breaks down into smaller irreducible groups, which means irreducible pieces, which means large number of particles which were actually one particle before. Of course, if you go the other way, what you see is you have a broken symmetry where different particles look like different particles, and then when you unify them, that is, when you go back to a regime where the symmetry is no longer broken, you see that those are really the same particle. They have got unified. So this is really the basic mathematics behind unification and broken symmetry. Okay. Of course, there's more to it than this, but this really is the core maths there. So, of course, one important question is, okay, this is, say, the two-dimensional representation is reducible, of course. And in this particular example, it's very easy. It has to break into two of the 1D irreps of the rectangle. Of course, for that, you need to know what the irreps of the rectangle are, and you have to form the character table. Okay, can you quickly form the character table for the rectangle? That is, you have 4 classes, and here I can directly label the classes by their elements. There's just one. So chi1, maybe I should really try drawing a more vertical line. Okay, this is pen, but still. Okay, quickly, can we form the character table for this? This is very easy. An abelian group is always easy. All 1D representations, so this column, of course, is all ones because that's just the dimensionality. And one irrep is for free. Everything 1 is always there. Okay, what about the rest? What do you know about the character for A?
Plus or minus 1.
Sorry.
Sorry.
Hello?
Sir, since we saw that the representations can be the specifically the representations which are conserved, like which are not broken, can be directly taken from the bigger symmetry to the smaller symmetry group. Then we can just take the character table as well. Right? Take just the elements that are.
Okay, so what you're saying is you just take the character table for the bigger group, just push them in, right?
Yeah.
Well, if you remember, in the bigger symmetry group, A and B were in the same class, right? Because A and B were in the same class, A and B would always have to have the same character, right?
Yes.
So if you went by that, you would only have either both 1 or both -1. But if you do that, AB is G, right? So chi A, chi B has to be chi G. Remember, for 1D representations, characters are just group elements. So you will end up with this.
Right.
And what's wrong with that? What is wrong with that?
Well, A and B, they are.
Well, what is wrong? Why is this not the character table? Just tell me what's wrong with this character table.
Orthogonality doesn't hold.
Well, of course it doesn't hold, but the real reason is you don't have 4 different irreps, right? You have only 2. The second row and the fourth row are identical. The second row is identical to the first, third row is, and fourth row are identical, right? What you have managed to do is write down 2 irreps this way. Not all of them. Do you get my point? What I'm trying to say is, while your attempt was not bad, but remember one thing: while the irreps, those are just the irreps, right? You just took all the irreps which were one-dimensional, just plucked out the ABG relations from that, and you should say that there will be the irreps for this new thing. And you are right; these will be the irreps. Nobody told you that these will be all the irreps. That's it. So what is the correct table? Okay, the correct table is actually pretty easy. In fact, it's easier. If you did not know those other results, it would have been perhaps been able to arrive at this much faster. A, what are the possible characters for A? Just quickly. What are the possible ones?
Plus or minus 1.
Right. And what are the possible characters for B? Plus or minus 1 again. And now that they are in different classes, there is no reason why they have to have the same character. Is it okay? In the earlier version, for the square, A and B belong to the same class, which forced them to have the same character. Now A and B can very well have different characters. And you have 4 possibilities done. And G, of course, is not independent. G is AB. So that gives you this. That's your character table. Okay. The only problem, if I had not told you the squares character table first and then talked about the rectangle, I had just given you the rectangle character table to find out, I'm pretty sure this would have been a trivial thing to do in 2 seconds. Identity always 1, A and B squared to 1, so must have either plus 1 or minus 1. So that gives you 4 choices. Done. Remember, we said this also for the square. We had A and B have 4 choices, C and D have 4 choices. So if everything had independent choices there, you would have ended up with 16 different rows. 2 choices each for A, B, C, and D. The reason why you don't get 16 choices there is that AB must have the same choice, so that's only, and CD must have the same choice. Okay, and F, G, H are not independent choices. The moment you fix A, B, C, D, F, G, H follows from there. So AB, 2 choices, CD, 2 choices. That's again 4 of those are the 4 irreps done there. Here, it's as simple as this. Everybody with me so far? That was a question. It didn't sound like a question. I guess it sounded more like a statement, but
yes.
So the 4 irreps. The irreps of the square will give you irreps, at least for one-dimensional cases. There's no choice really. A one-dimensional representation for the square has to be a 1D representation of the rectangle, and 1D representations have to be irreps. Okay. The only point is they don't have to give you all the irreps. In particular, if you look at the 4 1D representations for the square, which ones do you think will not be represented here as irreps?
Sir, can you repeat the question?
As I said, you take any representation of the symmetry group of the square. I'm saying representation of the square, just to shorten the words. You take any representation of the square, pick out EABG representatives from them. That should give you a representation of the rectangle. That much we settled. If it's a 1D representation on the square, it has to give you a 1D representation of the rectangle as well. And 1D representations are always irreducible. No question. Because how can you reduce a 1D? It's already the smallest size. So now the question that I have for you is, if you take this 1D representation on the square, then you have 4 such 1D representations for the square. They will not give you all the 4 irreps here. They will only give you 2 of them. Question is, can you say which ones among 1, 2, 3? Let's call them these gamma 1, gamma 2, gamma 3, and gamma 4. These are the 4. Sorry, I put everything too close. gamma 3 and gamma 4. Here the representation and the character of course is identical because these are all 1D. But among the 5 here in this table, I know among D1, D2, D3, D4, D5, the first 4 have to give you irreps for this. Okay? There's no choice. And the last one has to be a reducible representation. Again, no choice. But the question I have for you is just this. If you take this one, for example, E has character 1, G has character 1, AB has characters 1 each. So which one is that? Here? T1 has to be a irrep here. Which one?
Gamma 1.
Of course, gamma 1. But my question is, if you took D1, D2, D3, D4, which ones among gamma 1, gamma 2, gamma 3 and gamma 4 could not figure there? For example, can you have D2 equal to gamma 2?
Yeah, gamma 2 and gamma 3 won't fit in there.
Gamma 2 and gamma 3 will never come. Why? Because gamma 2 and gamma 3 have different characters for A and B. And no matter what you do in the original square, they had same character. So if at D2, okay, let's just remind ourselves what D2 is. D2 is 1, again 1, 1, 1, 1. If you just look at the first 4, that's it. So D2 is actually also gamma 1. That is, D2 reduces to gamma 1. D3 and D4 actually reduces to gamma 4. Both. None of the 1D reps of the square reduce to D2 and D3. By the way, these are the important significances. Not this square to rectangle, but this issue of breaking a bigger symmetry down to smaller symmetry and looking at the irreps, which ones are still represented, which ones are not. That actually has big consequences for, say, the particle structure and interactions possible when you reduce the symmetry. Okay, so that's an advertisement for the future, but you have to realize that those things, which many of the results which you get in broken symmetry, they are things which are basically group theoretical results. If you knew the group theory behind it, those results would be sort of trivial to see. Well, what about D2? D2, of course, sorry, D5. D2 is done. That's a 5-dimensional representation which had, sorry, 2-dimensional representation which had 2 minus 2. Right? Which had so can you tell me what D5 is? D5 is a reducible representation, was a reduction.
Sir, minus 2 is for G, right?
Yeah. Didn't I put it? Oh, I put it in the wrong place. I ordered it wrongly here. I should have actually put G next. Anyway, you're right. You're right. It is 0, 0, minus 2. And that's actually important because if you do it for the wrong value, you'll of course get completely wrong results. Gamma 1. So D5 is? Tell me, what is D5 going to be?
Gamma 2 plus gamma 3.
Gamma 2 plus gamma 3.
Yeah, exactly. The two irreps which were not showing up among the 1D irreps, D5 actually has both of them. Okay. Now, can you see why D5 has to have both of them? Any simple logical reason why D5 has to have gamma 2, has to be gamma 2 plus gamma 3? I could write that down without even looking at the character table. After I know that D1, D2 is gamma 1 and D3, D4 is gamma 4.
The additional symmetry of the square coupled these two gamma 2 and gamma 3 into 1.
I would say it's even easier than that. Look, if you take an arbitrary representation for the square, you end up with an arbitrary representation for the rectangle. If you just stick to EABG. So arbitrary representation of the rectangle must have gamma 1, gamma 2, gamma 3, gamma 4, all of them. And any representation of the square, what is that? That something can break up into D1, D2, D3, D4, D5. And if D5 did not have both gamma 2 and gamma 3, then there would be no way you would get gamma 2, gamma 3 in the rectangle. That would be a disaster. That you are saying you have erupts which are never represented. That's of course impossible. Erupts are representations. Just think about it a bit. The fact that gamma 1s are both gone in gamma 1 and gamma 4 are both gone in the Fundy representations. The one erupt which square still has left must have the other two, and since it's two-dimensional, must have gamma 2 plus gamma 3. There's no other option. But the point I'm trying to make is, this is very simple maths, but this very simple maths actually leads to other important consequences wherever broken symmetry comes about. Okay. Now today I don't have much time left, but what I will do is I will set up stage for one important result which is almost never taught. This is one thing which I have never taught before, I guess, in a class. I definitely didn't teach you in the group theory class for representations, which is okay. We have talked about how to calculate the character table, right? But you should realize that that method that we talked about, it looked like an algorithm to you. Of course, to answer this question, you have to precisely know what an algorithm is. So what is an algorithm, by the way?
Sequence of steps that you follow.
But where does it lead to? It's not just a sequence of steps that you can follow. That's not all all that an algorithm is. The sequence of steps that you follow to get what? Okay, that's the point, a desired result. And one critically important property of an algorithm is, within a finite number of steps, it should tell me whether I've got that result or I cannot get that result. An algorithm could be restrictive in the sense that I can only call something an algorithm if it gives me the result in a finite number of steps. But sometimes I can also call something an algorithm which either gives me the result in a finite number of steps or tells me that this result cannot be obtained. End of story. Okay. Finiteness is important in an algorithm. And you don't have to go beyond that. But if you realize the way we created the character table so far, we did not really have an algorithm as such. What did we do? We just used some basic principles, wrote down the character table as much as we could, and then when we did not get that just from the orthogonality relation, then we tried to say, okay, let's look at the group multiplication table, let's do this, let's do that, and with very simple manipulations found the result. Okay? Like the statement that A square is identity, so chi A has to be plus minus 1. Then go to the fact that A and B are in the same class for the square, so chi A has to be equal to chi B, and so on. And chi F has to be chi A into chi C or whatever. Okay? So this kind of statement, this kind of method works, but you should realize that there's a bit of a hit and trial thing about it. In the sense that there's no guarantee that given a big group, I would be able to find out all its errors or the full character table just by keeping on doing this kind of argument. There's no rule which says you do this, after that you do that, after that you do that, and after say 5 steps you get the result. Do you see my point? We were playing around, of course, because we were not dealing with a very complicated group. It seemed all very nice and we managed to get the result. Okay. But given say an arbitrary complex huge group with maybe 50 classes, so 50 errors to work with, can we write down and figure out a method which will tell me that at the end of this step I've got the full character table? This one wasn't that. At least that you should realize. We did use some basic ingredients, but we did not really use them in a very regular sequential way. We just did whatever came to our heads and it worked. There are actually algorithmic methods which you can use for large groups. Why do I say large groups? You can of course use them for all groups, but for small groups like the symmetry group for a square or the rectangle, the non-algorithmic method that we talked about now earlier, that actually works faster. But for big groups, that result that may not even work at all, but the algorithmic methods work. So I will try explaining that in the next lecture, exactly how to write down an algorithmic method and which will always give you the result. And because then we are going to, and that is one good thing about that is you can put that on a computer. You can actually make the computer program, write down a computer program, which when you feed it the group multiplication table or that in some other form, essentially something called a class multiplication table, will give you the character table complete. Okay, so that's actually an important thing to know. In most physics applications, not all, but in most, we hardly ever meet very complicated, difficult groups. So physicists don't tend to learn about them all that much. Of course, that's really not true in the sense that solid state physics, for example, has many situations where complicated groups are met, especially in a crystal lattice. So in solid state physics, most of the standard crystallographic point groups have already, not most, all of them have been tabulated, so people look up a table. So you may say that you don't really need to learn this method, but it's an interesting method, and sometimes even for not very complicated groups, this method actually helps you to do the calculation a lot faster. Okay. Okay, so let me just ask you, do you think it's worth learning this, or can we drop this issue? Because as I said, physicists can often survive without knowing this, because the hard work usually has been done by somebody or the other, but that actually is, if you just rely on that, that would also be a bit sort of like the same objection that we have for using group theory in chemistry. There, of course, most chemists don't really know the great orthogonality theorem, but they don't need to. They have a character table, they know what the rules are. So, okay, I'm asking you for your opinion. Do you really think that it's worth learning about it? It will take one class or two to learn about it.
I mean, it would be helpful, like just as a general knowledge. So maybe then.
Yeah, it may be useful more as a general knowledge. It may be useful specifically for your application someday, but you never know.
So you can just like 1 or 2 classes, like a short intro or something.
Okay. Okay. So today what I will do is I will just set up the basic group theoretical result, the abstract group theory result, which is going to come in useful here, because I don't have much time left today. Also, this is a very important result. This result I would have taught you anyway, because even if you're not going to learn the full algorithm, this result often comes in handy. And just to illustrate that result, what I will do is go back to the square case, talk of the classes. So we had labels for these classes, right? We call this C1, and for G, we call G C2, right? It doesn't matter, anyways, C3, C4, and F and H, this is C5. Now, we did introduce this before, how to multiply two subsets, right? How do you multiply two subsets A and B? You just form all the product AB for all A taken from A and B taken from B, right? Is that okay? You remember this, right? This is how you multiply sets. Now, the question is, if you multiplied AB, let's say with CD, what will you get? How many elements will you get in the set? That's a difficult question. It looks like 4, but it may not be 4. So what you are forming is AC, AD, BC, BD. What will you get? Anybody tell me the answer? AC, two reflections with planes at 45 degrees to each other. Result has to be a rotation, right? Done one after the other. Which rotation?
F, I guess.
F or H depends on which order you take them in. But anyway, F or H. But you should realize all of them give you F or H, right? After all, AC, AD, BC, BD, all of them are, well, planes separated by 45 degrees. Either plus 45 or minus 45. Two successive reflections will always give you a rotation through either 90 or minus 90, F or H. Okay? So if you think in other classes, you get C2 into C3 is C5. Right? What is C2 times C2? AB times AB. What is that? Okay, sorry, C2. No, sorry, this is not C2, C3. I apologize, my labeling, I got screwed up. This one is, in my labeling, this is C3 times C4 is C5. Yeah.
Sir, I just wanted to say something. This won't. We still have a Lie algebra and a lot of stuff to cover. So this.
Okay, so you're saying we can.
I don't know how to say.
You're saying that it's better that we skip the algorithmic part because we don't have time to cover the physics part. Is that what you're saying?
No, not like that. If you can arrange 2 extra classes, that will also work.
Maybe we'll see about that. But okay, anyway, this result that I'm talking about you will need anyway. So whether we go on to the full algorithm or not, but this is something you will need sometime down the line in an application. So this is better to learn at least this much. Okay, this is trivial. Of course, you know that C3 times C4 is easy to calculate. You get C5. But what about C3 square? Can anybody tell me that? What is C3 square?
C1.
No, it's not C1. It is C1.
C2.
C1 is there.
C2.
Is it C1 or C2? Why do you say C2? Why not C1? AB times AB. That's A times A times B, B times A, B times B. It's actually C1.
It's C1
and C2. This plus really means the two sets taken together. Okay. Right? But now let's look at the number of elements. If you look at it, there is actually 2 C5. That is, C5 is coming in the, when you multiply C3 times C4, C3 times C4 will give you 4 elements. Out of the 4 elements, C5 comes twice, that is F comes twice, H comes twice. So this is 2 C5 really. There is not a union. This is, you are really counting how many times the real element comes. Okay? Here what happens, C3 square, C1 comes twice, C2 comes twice. Right? A times A is E, that's C1. B times B is E, that's C1. So that's 2 C1. C1 comes twice. C2, how many times does C2 come? A times B is G, B times A is also G. So that's 2 C2. Right? Got it? So this,
yes.
Now the critically important thing is, for any group, if you have 2 classes C and C prime and you multiply them together, what are you going to get? Now this is a bit tricky. Now this is something, okay, I don't have the time to do it today. So this is a homework. Try to prove for yourselves that in the product CC prime, either a whole class will appear, well, more than one class may appear in the product. But if a class appears, then every element of that class appears. Okay? Do you get that point? It's not possible, for example, to have something like this. If you multiply any of the groups here, you cannot get something like A and C, and only A and C. If A comes, B has to come, because A and B are in the same class. They will always be there. If C is there, D will also have to be there. Okay? So this is a result which is actually pretty easy to prove. I will ask you to prove this and the corresponding result, that in this particular context, if A appears 4 times when you multiply a class, B will also appear 4 times. If G appears, G is of course on a class of its own, but if C appears 3 times, then D will also have to appear 3 times. That is, every class has to appear as a whole number of times. If it appears at all, a particular class may not appear, but it's always possible to write this as okay. This is a result. This is a result from group theory. This has nothing to do with representations. If you multiply 2 classes, the resulting thing always is the integer number of full classes occurring. That integer could be 0. A particular class may not occur. But if a class occurs, every element of the class has to occur equal number of times. Very easy result to prove. Try proving it. Now this actually comes in very handy because, well, if you think in terms of characters, then characters of course are the same for every element of the class, and using that result you can get a very important equation which will relate characters of classes. I will come to, okay, I may not go to the full algorithmic method the next day, but at least the basic equation, which takes around 5-10 minutes to talk about, will indicate that. That will tell you how to write down an algorithmic method rather easily. That method has some pitfalls. It's although it's an algorithmic method, it's not really very stable. Numerically, it may give problems. So there are other improvements on that. I'm not going to talk about that improvement. But this one method, which actually is pretty useful, because very often in many calculations we may have to actually use this. So we will talk about that in the next class. But the question is, when is the next class? Tuesday is fine for you, or are you all going to take this autumn break seriously? Yes? Now this is a tricky question, I understand. So we have an autumn break from when? From Monday to Saturday, right? Next week?
19th October.
No, that's a Monday, I hope. 19th to 26th or 25th, right? 19th to 23rd, because 24, 25 is holiday anyway. So do you want to have a class on Tuesday? Yes or no? Thursday we may not have a class, but Tuesday can we have a class? Yes or no? Okay, if anybody has a no, just say that. I'm pretty sure everybody is waiting for somebody else to say no.
So,
anybody?
So we'll
Yeah.
get back to you later on after the after the class.
After fighting among yourselves.
Yes.
Okay, fine. Okay, so let's call it a day today. Next week, if we have a class on Tuesday, fine. If we don't, then of course we'll meet the Tuesday after that. Although, wait a minute, the Tuesday after that is what day? Tuesday after that is fine, I guess, because that's 27th. But next week I have the week after that I have no problems. The week after that I'm actually talking about group theory in an Assam University webinar, so, or a workshop. So I'm really engaged on all 3 days then. 3rd, 4th and 5th. Although, no, I'm engaged in the afternoon, so I can still have a morning class. Not a problem. Okay, fine. So just let me know. But let me know soon. Okay? So fight out among yourselves, let me know. Okay, I shouldn't have recorded this. Anyway. So bye for today. Next day we are going to take a look at just a small part of this and then move on to actual applications.